Okay, so this is the third in the series of spatial panel regressions, and this one deals specifically with spatially seemingly unrelated regressions. So seemingly unrelated regressions are a classic tool in econometrics to take advantage of some cross-equation correlation, so to speak, but they have an interesting application in the spatial field in that they allow us to implement a form of spatial, actually temporal fixed effects, which goes beyond the dummy variables that we've done so far. So when we saw the fixed effects and random effects models last time, in the cross-sectional setting, we typically introduce a dummy variable to capture the temporal effects. But as I pointed out then, these dummy variables only capture shift and intercept. They don't actually affect the slope. So now we're going a little bit further and allow both the intercept and the slope to vary from time period to time period, which then opens up a number of new possibilities of testing. So we're going to start by going over in a sense, what is special about a spatial, seemingly unrelated regression setup, and it's very much along the same lines of what I mentioned before. It's the flipping. So in the traditional setup, you have the vertical focus on the time series dimension. In the spatial regression, we focus on the cross-sectional dimension. And so I start with the standard setup, so no extra spatial effects, just a spatial organization of the data, the standard estimation methods, feasible generalized least squares and three-stage least squares, and then two special types of tests. One is a test on the diagonality of the cross-equation covariance matrix. So in other words, is there an advantage to doing this? If there is no cross-equation correlation, then we shouldn't bother. Then we should just pool everything. And along the same lines, a test on the coefficient homogeneity. And again, if there is no difference between the coefficients at different points in time, we should just pool them and run the whole thing together. So that's really the main advantage of doing this, is it allows us to test different types of hypotheses without really having to specify a very precise model for the temporal correlation. And this is very useful in treatment effect analysis. So in treatment effect analysis, you often have a design that is a before and after. So you have a relationship before a policy and a relationship after a policy, and then you can test, even with a difference in difference setup, where you have a control group and a treatment group, you can look before and after at coefficient differences between the treatment group and the control group. So it allows you a very flexible setup for these kinds of tests while accounting for everything under the sun, right? Spatial dependence, spatial heterogeneity, heteroscedasticity, all that fun stuff, endogeneity, all these things. So then, after the kind of the basic model, which is in essence just what you get in a standard econometrics text, but flipped sideways, and then we go into the specific spatial models, the lag and the error model. And for both, we have two basic estimation strategies. One is maximum likelihood, which is a pain in the neck, but it's good, it's just kind of to put things into perspective. And it also provides us the basis for Lagrange multiplier testing, because the Lagrange multiplier testing is based on the likelihood paradigm, if you wish. And then the other estimation strategy does not assume a full distribution, does not assume normality, and is either based on a generalization of two-stage least squares or on a generalization of the generalized moments, the GM approach that we've already seen before in the error model. So in terms of the readings, same thing as before, the chapter, but there's a kind of a technical report that I put together, which really is the technical guideline to the code that we're in the process of developing. Some of this code is already part of PyCell SPDEP, but some of it we're still finalizing. It's not quite out yet. We hope to have it out by the summer. And then, as I mentioned the other day, the goal is to have all this incorporated into GeoDa proper, at some point. So let's start with the standard model. So the model specification in the classic model was really about having different time series and modeling the correlation between the time series, which is therefore cross-sectional correlation, in a non-parametric way. And the classic example, you may be familiar with this, is referred to as the Grunfeld example. It's a sample of an investment by a number of companies, GE and then a couple of others. So there's a time series for each of these companies of an investment function, and then the error terms are assumed to be correlated between firms, but without imposing a particular structure on that correlation. So in essence, the correlation comes from a standard correlation between the residuals of these two regressions. So the main idea in the classic textbook SUR model, SUR model, is that the cross-sectional correlation is non-parametric. So you don't need a model for it. So these could be, for example, other examples besides the investment equation would be in regional economics. Say if you have some labor participation equation for 4 or 5 different regions in the country, and they're based on time series, then instead of specifying a weights matrix, which is what we've been doing, you just get the time dimension to give you the cross-sectional correlations in a non-parametric way. And in fact, some of the new and exciting literature on spatial panels kind of extends this idea to situations where both n and t are large. So when both n and t are large, you can use some of the correlations between the time series to give you a non-parametric sense of the spatial correlation. And then the question is this better than imposing a weight matrix, for example? And so there's a couple of really interesting papers dealing with that. So that's the traditional setup, which emphasizes the time series dimension. So in the spatial setup, it's flipped around. So rather than having a time series for each cross-sectional unit, we have a cross-sectional series, if you wish, for each time period. And so rather than having a non-parametric, unspecified cross-sectional correlation, we now have a non-parametric, unspecified serial correlation. So the correlation between different time periods will come from the correlation between the residuals at different time periods for the cross-sections at different time periods. So instead of having what we have in the classic model, sigma ij for the cross-equation residual or error correlation, so the error terms between two cross-sections I and j at time t, for any time t, for all the time t, is a constant. Then in the spatial setup is the same thing, but flipped around. So the correlation between two different time periods for any I and all the I is constant sigma ts. So there is some structure built into it, which is unavoidable, is that this correlation, the serial correlation, is constant across cross-sectional units. So the effect over time is the same across cross-sectional units. But keep in mind, this is for the error term, right? So there's all kinds of other dynamics. We didn't get into this because we've been focusing on, static, pure cross-sectional panel data, but with dynamics, you can have all kinds of lag terms in these equations for each time period. It just makes everything more complicated. But so it's not that this kind of somehow limits the structure of the serial correlation. You can bring in more complex things as well, but as a point of departure, this is the temporal error correlation for across the whole cross-section. So for time periods t and s, that's sigma ts. Now, just as an aside, in time series correlation, we typically have this decay. As time periods are further away, the correlation is smaller. This doesn't guarantee that. So typically this holds. I mean, in the empirical examples that I've worked with, I haven't seen any counterintuitive results in that regard, as opposed to in the classic SIR, where if you have cross-sectional units, that you do see covariances that are not necessarily decaying with geographical distance. And that is because oftentimes, geographical distance may be secondary to network distance, for example. If you do the correlation between New York City and LA, it's going to be a lot stronger than between New York City and, say, Pittsburgh, even though Pittsburgh is a lot closer. Right? So that's something to keep in mind. But in a time domain, you don't really have this complexity. It should really, if it doesn't decay with increasing time distance, then something's wrong, typically. Okay, so how do we set this up? As I mentioned, this is much more general than having a different intercept at different points in time. We actually have a different equation for each time period. So you see the beta has a subscript t. So for every t, for every time period, you will have a different beta. So think of this in the context of my example, my homicide example. We have data for 4 time periods. Each of these time periods is a different regression. And what we're interested in is contrasting this viewpoint, which is really a temporal fixed effect viewpoint, to the viewpoint that we had before, which is where we forced the beta to be the same over the different time periods. So both in the naively pooled regression that we did in the first lecture, as well as in the fixed effects and random effects that we did a couple days ago, beta was the focus of interest. Here, we have a different beta at each point in time, which includes the constant term. So we can test all kinds of things. Which of these coefficients are essentially the same over time, and which of these are clearly different. And then the cross-equation correlation, now pertaining to 2 different points in time, is based on the error term. So to keep it simple, in this case, the cross-equation correlation is constant. That's where we have the identity matrix. So this is the point of departure. Later, we'll make that more complicated. So as I mentioned a few minutes ago, this cross-equation, cross-time covariance is constant across the cross-section. And it's non-parametric. The data, in the sense that the data, now obviously the error term is not data, but we'll use the residuals to get at this. The data will determine what the magnitude is, no model. So in terms of actual implementation, the key is that we run this as if this was one single regression, even though it's really a system of different equations. So you can think of this, each row of this corresponds to a different time period. We just stack them together. There's lots of zeros here, only the diagonals matter, but then we can run this as one huge regression of nt by 1 vector on this side, and this is actually not nt by k as we had before, but nt by k by t, assuming that k is constant. The other thing that you have in this model, which we didn't have before, is that the explanatory variables can be different at different points in time. So the k does not have to be the same at each point in time, which again allows some more flexibility. And then we can write the big, covariance between all of these again, in Kronecker form, if we think of this again, this is a T by T matrix of time-wise covariances. And so for each of these, we have an identity matrix of dimension n. So at the end, this becomes nt by nt, which is huge. Right? So nt by nt is the full dimension of the panel, but we get at this with two pieces. One piece pertains to the time dimension only. It's very small typically. The other piece is large, but it's an identity matrix, so we don't really have to worry about it too much. So we think of this as a system, and then we estimate this in one big shot. So why would we do this? As I mentioned, it's a generalization of temporal fixed effects, in that we go beyond just the intercept and also allow the slope to vary over time. We can have different coefficients in each time. And an original motivation for this, which is actually, as I mentioned a lot of times, as we move to a big data world that is less and less really critical, this is the efficiency gain from exploiting the cross-equation covariance. You can think of this as a similar rationale as generalized least squares. But for some, if you do some algebra, you can actually show that this only works if the xt are different in each time period. So for example, this would not work in a design where your left-hand side changes over time, but the right-hand side does not. Some time ago, somebody sent me really interesting electoral results for Argentina, and he had the results for 4 or 5 elections in a row, but he only had the census data at one point in time. So that's a design where this would not work, because you did not have changing x's for each point in time. And it's not always obvious, but you often get stung by this if you have a dependent variable that is measured at a much greater frequency over time than the explanatory variables. It's going to limit what you can do with this. The estimation is about straightforward as it can be. You just think of this as a special case of something that we've seen many, many times before, a non-spherical errors variance covariance matrix. That means the variance covariance matrix is not diagonal. And so that's where the testing for diagonality makes sense, because if it is in fact diagonal, this doesn't help. Then you just do each equation by itself. There's no gain from grouping them together, right? But if it is non-diagonal, then you can think of this as a generalized least squares type of setup, and in fact specifically, as we already know, feasible generalized least squares, which means we need to have a consistent estimate for the variance covariance matrix, and although at first sight that seems a little impossible, it is only a T by T matrix that we need to specify. So that's definitely possible in a design with a large n and a short t. So the general expression is the feasible generalized least squares expression, x prime, the inverse of the covariance matrix, x, the whole thing inverted, and then the same thing here but with y. And we take advantage of these Kronecker properties that this inverse of an nt by nt matrix in fact boils down to the inverse of a t by t matrix, which is much smaller, with the Kronecker that extends this. Right? The estimate that we get, and we can prove all this stuff, is actually very simple. So you get the residuals for each time period, and you just take their covariance, and you estimate their covariance, and that's it. That's a consistent estimate for sigma ts. And so once you have this, then you can plug this into the sigma hat, and you're in business. You have the estimate, and this is the traditional variance. So this suggests a two-step process. In the first step, you get residuals. Then you use these residuals to estimate these cross-equation covariances. Then in the second step, you do a feasible generalized least squares. And the residuals, again, I won't dwell on this, but this can be proven that the residuals can be either OLS residuals or two-stage least squares residuals. So you can generalize this to situations where you have endogenous explanatory variables. So just to illustrate this, and I purposely don't have a lab or a practicum because this stuff is still under development and it works, and you know, people are using it for real applications, but it's still a little picky, I should say. So this is an example of a two-step, just simple, run OLS, get the residuals, estimate the residual covariance, this is the correlation, then use this in the second step in a feasible generalized least square. So this is just our standard homicide example applied to two periods. And there is a very old proof that shows that if you iterate this feasible generalized least squares, at the end you get an estimate that is equivalent to maximum likelihood. And so we can iterate this, and this is the same model but iterated, and just to give you a sense, this isn't dramatic, right? Here we have 0.507 as a correlation, and here we have 0.469. So there's just teeny little differences. If we look at the coefficients up here, you know, 5.139, 0.677, 5.184, 0.677. So these are minor differences. There are minor differences in the variances as well. I won't talk about this yet. The main difference between the two is that because the iterated result is equivalent to maximum likelihood, you can use maximum likelihood based tests like Lagrange multiplier tests, which we'll get to later. So you see them here, they work, but we'll get to them after we talk about the maximum likelihood estimation. So the principle is very simple. It's a two-step or multi-step procedure. You run standard OLS, you get the residuals, you estimate the covariance matrix, then you do feasible generalized least squares, and if you want to, you keep doing this till it converges. So then the generalization of this to a situation where you have endogenous variables on the right-hand side is three-stage least squares. And you're probably familiar with this, but it's just again, you can think of this as the different equations. The z now include both exogenous and endogenous variables, so they're stacked on the diagonal. The whole structure is exactly the same, but there is an extra step. So the extra step is that we need the instruments. So just like in two-stage least squares, we get this, these matrix, I call these the instruments, then they create the instrumental variables. So the instruments, there are more instruments than instrumental variables. Instrumental variables is 1 for 1. If you have one endogenous variable, you have one instrumental variable for that, which in a sense replaces it in the estimation process. And that instrumental variable is the predicted value of the regression of all the instruments on the original set of variables. So you get all this in there. You replace z in the expression for feasible generalized least squares by these z hats, these predicted values, and everything else is the same. So there's one extra step, just like in two-stage least squares, but you don't actually have to do it in two steps. You can do it all in one very long expression with a lot of matrix multiplications, but it's basically always the same idea. You replace the endogenous variable by a predicted value that is no longer correlated with the error term, so then you're fine. So the three-stage least squares is actually a three-step procedure. You do two-stage least squares on each equation. you get the residuals, you compute the cross-equation covariance from the residuals, and then you plug that in here on the whole system. So there's a lot of literature, or I should say there was a lot of literature quite a while ago on which instruments one should use. So in other words, should the instruments be equation specific? In our case, that is time specific. Or should you use all the instruments from all the equations? So in other words, specifically, if we have the same endogenous variable in each time period, should we use only the time specific? So for 1960, we use 1960 instruments. 1970, we use 1970 instruments. Or should we use all the instruments? So for 1960, we use 60, 70, 80, and all of them, right? And there's some interesting papers looking at efficiency gains. One you do get them, one you don't get them. Basically, you know, as we already know, at the end of the day, it doesn't really matter that much because the main thing is these instruments will all be uncorrelated with the error term by construction, and the adding more instruments can give you efficiency gains, but only up to a point. As I said many times before, if your predicted value becomes too close to the original, then it inherits the problems of the original, and then you lose the lack of correlation with the error term. So that kind of defeats the purpose. So it's not necessarily a good thing to just load up on instruments. I mean, you have to really think about that. At some point, as the, you know, in a sense, the match between the instruments and the original endogenous variable becomes too good, then it's no longer uncorrelated with the error term. So that's something, there's some interesting papers that show you the trade-off actually in simulated setups. So then the standard three-stage least squares estimation, here again an example, two time periods. And I'm just showing this to you to see the kind of stuff you get. So you see these coefficients actually for some of the variables are quite different between the years. We see these two, dv and ue, are taken as endogenous. And in this particular case, I'm using only instruments of that same time period. So each of these, even though these are listed as if they are two separate equations, they're actually all estimated together. So it's all estimated in one shot. The output is the result for each time period. So if you have 4 time periods, there are 4 results. If you have 2, there's only 2. So then we have the specification. The main is basically a classic textbook result, but everything is flipped sideways instead of vertical. The estimation, feasible generalized least squares, or iterating, which gives you a maximum likelihood equivalent. And then if you have endogeneity, you do 3-stage least squares. Then these specification tests, as I mentioned before, there are 2 main classes of specification tests. The first class is really to check whether you should even bother with this, right? So this only works if there is in fact cross-equation covariance, cross-equation correlation. So the null hypothesis is that the off-diagonal elements of sigma are 0. In other words, sigma is a diagonal matrix. So the equations are in fact uncorrelated, the error terms of the equations. So we have 2 ways of going about this. These are classic textbook results, and they generalize very nicely to the spatial models. One is a likelihood ratio test, and if you remember, the likelihood ratio test is about the difference between the constrained and the unconstrained likelihood, maximized likelihood. And with a little bit of algebra, we can show that this boils down to the determinant of the t by t sigma matrix that we estimate, and here the sum of the residual variances estimates for each of the time periods. So this is the constrained version. This is, you know, so you set the off-diagonal elements to 0, so each equation has its own error variance, you add them up, and then you compare this to the unconstrained version, which is when you have a full T by T matrix and you take the determinant. And then there is also a Lagrange multiplier test, which is in the same family as the Breusch-Pagan test. In fact, it's a Breusch-Pagan paper, which is very easy to do. R is the correlation matrix. That's the one I showed you in the output before. So you take R prime R and you take the trace, which is the sum of the diagonals, and you take the difference with T. Both of these are chi-square with T times T minus 1 over 2 degrees of freedom. So that's, if you have 3 equations, that is 6 divided by 2, so 3 degrees of freedom. Right? So then, just to give you a more complex example, this is a 4-equation system. These are the correlations. You see how nice they decay with time period. So, you know, if you just look at the first row, that's the correlation between time 1 and time 2, time 1 and time 3, and time 1 and time 4, and you see it nicely goes down. So we use this matrix. Either we take the log of its determinant, or, of the covariance. This is the correlation. So the covariance is just the correlation scaled. And then in the Lagrange multiplier test, we take this as well. You see, these things are huge. 4 equations, so 4 times 3 is 12, divided by 2 is 6 degrees of freedom. So this is just, way, way, way correlated. It's not always the case, I need to add, right? In this case, there is, these are long periods, right? These are 10 years apart. And in this particular context, it's about homicides in the US. And there were some major things going on in that, 30-year period, like the crack epidemic and then the crackdown on the crack epidemic. So there were some major migrations of crime basically in the country. And if you look at it as a time series, it goes up, it goes down, and then, and it's flat basically. So there are big things going on between these time periods, so you would expect some correlation. So that's the first type of test, which is basically about whether you should even bother with this. And the second type of test is actually much more interesting. And this is where the treatment effects come in, the difference in different design possibilities come in. The null hypothesis is that for any given coefficient, the values over time are the same. So in that case, there is no advantage to having temporal fixed effects. You should just pool, and we're back in the situation we had the last 2 lectures with one given beta, one beta for all periods, right? And so you can write this, and we do this on purpose to make this fit into a general Wald testing framework, which is a test on linear constraints on the coefficients. So we can write this as a 0 constraint. So beta is really big. Beta is each equation at a time, all the coefficients. So this is an equation, an example of beta for 3 equations with 2 coefficients. So you have 1, 1 and 1, 2. You have 2, 1 and 2, 2, and then you have 3, 1 and 3, 2. And so what are the kinds of constraints that we want to test? Whether, let's see if this is right. This is an example of a constraint where you test whether this one minus this one equals 0. So these 2 coefficients equal. And here's the second one times the last one equals 0. Right? So, and you can do this in general for any R that you want to set up, any type of equality or adding up constraint you want to test. For example, in a lot of the band equations, you're interested in the fact whether some coefficients, 2 or 3 coefficients add up to a value equal to 1 or not. And so then you can set this up in the same framework as a constraint on the coefficients. That's where a lot of the original SUR applications came from demand equations. By the way, this is developed by Arnold Zellner, who's better known as the founder, if you wish, of Bayesian econometrics. He was here at Chicago for a long time. But some of his early work was non-Bayesian. This is definitely non-Bayesian. So this is also called Zellner's seemingly unrelated regression. So then we can set this up in general, as I mentioned, as a test on the constraints of R, this matrix with 1s and -1s and 0s, times our vector of coefficients. And then in the middle is really the variance covariance matrix of the coefficients. So whichever one you get, pre and post multiplied by this R matrix. So it's very easy to do as long as you have the right R matrix, and of course as long as you have V. Now the reason I mention this is that in the spatial models, especially when we do maximum likelihood estimation, getting this variance covariance matrix is not trivial. So in those cases it may not be possible actually to carry out this test. So the two things we need is we need a good setup for the R, but this is perfectly general. It doesn't have to be, you know, simply the equality across equations. It could be many more things. And we need this V, and then we're in business. And this is an example in this particular case, clear evidence of rejection of the null. So in this case, there's absolutely no evidence that any of these coefficients are constant over the 4-year period. Okay, so now we move into the spatial models. And they're very straightforward. We've actually already seen most of the pieces. The only difference is that here, instead of having one autoregressive coefficient, one row that is constant over time, we allow the autoregressive coefficient to vary by time period. And so then we can introduce the autoregressive coefficient, the rho sub t, within this testing for homogeneity of the coefficients. So not only can we test whether the betas are constant over time, we can test whether the spatial effect, the spatial autoregressive coefficient, is constant over time. So the setup is pretty straightforward. We have our spatial lag model. We just call this A, our filter. And then this is always the same. So this is the cross-equation correlation with our sigma t. This is our system. The only thing that's different is that we have A here. And of course, A contains our parameters, the rho 1 through rho t. So there are t spatial autoregressive parameters in this model. How do we estimate this? As I mentioned earlier, there's two strategies. One is always maximum likelihood. The other one is not. And as a practical guide, the non-maximum likelihood route is the easier one to take. I will spare you the derivations if you want to see them. They're in that technical document, but it's a pain, okay? And they, as we already know, these maximum likelihood variance estimates tend to involve big matrices, I minus rho W inverse, et cetera, which are not trivial to compute for larger data sets. So the spatial lag 3-stage least squares is actually the easiest thing in the world because there's nothing special to it, right? Just like our spatial 2-stage least squares that we saw earlier for the spatial lag model is basically a 2-stage least squares, but with specific instruments. And so this one, same thing. We consider the lag term in addition to potentially other endogenous variables, this is perfectly general, as part of the endogenous. So the endogenous part potentially has two components. One is the regular endogenous that we just saw. The other one is our spatial lag term. And then everything else is the same. The only thing specific spatial is what are the instruments for the spatial lag. And here again, we take the spatially lagged x's, the spatially lagged explanatory variables, and then there's the same question as in general for three-stage least squares. Do we take these lags just for the same time, or do we also take the lags of the x variables of other time periods and bring those in? Right? And that's, I would say, an unresolved question. But it's very easy to do, and the result is something like this. In this example, I have 3 equations. You see W underline HR60, and we have in each of the equations the spatial lags of the exogenous variables. This is an example, just to give you a flavor of this, where we don't have the same number of explanatory variables in each equation. So this is perfectly general. You see in the second equation, I just did this randomly to illustrate the point. In the second equation, we have an additional PS70, which we don't have in 60 and in 80. You know. And so this may be a case that in some years you do have measurement available on some variable, in other years you do not. So you can allow for that situation. It's not the same as an unbalanced panel. See, an unbalanced panel, this is a form of unbalancing, but it's unbalancing in terms of the explanatory variables. In an unbalanced panel, it's unbalancing in terms of the observations. This is very much a balanced panel. It's the same cross-section each time, each point in time. And just to show you that we can, you know, this is throwing in more endogenous variables. And so you see, for example, here, this is exactly the same type of output that we had in the spatial two-stage least squares, where we applied two-stage least squares to the lag model. We have the instruments for the endogenous variables. So these are the 2 endogenous variables. They have their instruments. Then the spatial lag dependent variable is the other endogenous, and it has its instruments, which are the spatial lags, in this case, of both the exogenous variables and the instruments. As we saw when we talked about spatial lag estimation, you can either include the instruments in the spatial lag, but you don't have to, right? And so this is all straightforward application of general principles, except that, of course, if you remember my previous lectures, there's an easy part and there's a hard part, right? So the easy part is that it works out of the box just like anything else. The hard part is to demonstrate formally in proofs that this actually works in the spatial case, because the spatial case is more complex than the standard case because of these triangular arrays that you have to keep in mind. So there's a whole literature on this, on proving that this actually works, but once that's been done, it's really easy to do, and you don't even need any special software to do this. As long as you can compute your spatial lags of the exogenous variables, you can just use standard packages to do this. The maximum likelihood, the likelihood equation is a beast. So because it has a number of different parts to it, right? So this is, if you think of our full specification with all the equations, every time period stacked together in one big monster, this is kind of like a weighted least squares. These are the residuals. This rho is in here, the t rows are in here, the t vectors beta are in here, and the t by t sigma covariances are in here. And then, just like we have in the standard lag model, we have the determinant for the variance term and the determinant for our Jacobian, the Jacobian of the transformation that we need in the spatial lag model. So this determinant simplifies. I mean, it's in principle, it's the determinant of an NT by NT matrix, but because it's block diagonal, it simplifies to just the blocks, and because the blocks are all the same, it simplifies even more to the sum of t of these determinants, each with a different row t, but the structure is exactly the same. The difference between the pooled model that we saw or even the random effects models that we saw the other day, is that now we have a different rho t for each time period. That was not the case before. So basically, we play around with this a little bit. We use the fact that this is a consistent estimate for S. So then we replace sigma by this expression, and we do some algebra. Then, in essence, these terms, compensate for each other and boil down to just this log of the determinant of S, which is very simple, and then this term, which has the rho t in it. But now, I mean, this may look simple, but it isn't simple, because this is made up of these residuals, which made up of estimates for rho and beta, right? So there's actually a lot of parameters in this expression. There's, the t rows, the t vectors with the betas, and then the t by t, or half of t by t, variances and covariances. So that's the concentrated log likelihood. As it turns out, there is, just like, this was actually in my dissertation, this kind of shortcut. In the standard cross-sectional lag, you can show that the ultimate estimate of beta is basically a weighted sum of two separate betas. These betas don't change because there's no rho involved in here. There's one regression on y, the other regression on the spatial lag of y, and then here's the rho. And then we can do the same for the error term. So we can take advantage of this to simplify, in a sense, the maximum likelihood of the maximization process of the concentrated likelihood. So this can be done. The variance covariance matrix, as I said, is a bear, and if you want the details, you can look at the paper. Once we have all these pieces, when we have the likelihood and we have so we need the first partial derivative, the second partial derivatives, we need to replace them by their expected values. That gives us the information matrix. Then we take the inverse of that as the variance. So we can use all these pieces to build a LM test for spatial lag. Now, this LM test is not like we usually have 1 degree of freedom, because now we have t rho variables. So this so the null is that all t of the rho variables are 0. The alternative is that any one of them might be non-zero. So this is actually not the same as testing rho one equation at a time. It's all together, so it's enough that one of the t is different from 0 that you reject a null. So it's actually, in that sense, not that useful a test because it tends to reject all the time. So the first line here is the classic principle. We've seen this before. We have the so-called score, which is the first partial derivative of the log likelihood evaluated at the null. So we figure out all this very complicated partial derivatives, and then we make rho 0 in all these expressions. Then here we have the information matrix, which is the same thing. Second partial derivatives, very complicated, but at the end of the day, it simplifies greatly because we set rho equal to 0 in all these things. And then after a lot of algebra, this is the result, and I can still not write it out completely. This is the inverse of the information matrix, evaluated at rho 0. And then these two pieces correspond to the score, but these are actually much simpler than you think. So sigma hat inverse is a t by t matrix of the covariances that you estimate. So you estimate the covariances, you take the inverse of that matrix. And then this little star is a direct product. That's an element by element corresponding element product. So this is called, I don't know how they say it in English, but I call it a Hadamard product. So Hadamard. So it's a direct product, It's so 1, 1 with 1, 1, 1, 2 with 1, 2, 1, 3 with 1, 3, right? So then this thing here is also t by t. It's a little bit more complicated. So u is the residuals for each equation. So this is, for each equation, we have n residuals. So this is an n by t matrix. Y is an n by t matrix of the dependent variable. Wy is the spatial lag of this. And then this product is the transpose of an n by t, that's t by n, times n by t, which is t by t. So both of these are actually fairly small. If we have two equations, they're both 2 by 2. They look really formidable, but in the end, they're very compact, very small. And then you have this t by t matrix in the middle to make it a scalar. That's the spatial lag. Spatial error is a little bit more complicated. So the spatial lag, in essence, the only complicating factor was the Jacobian term, because the part that pertained to the residuals and the residual variance was all standard. That didn't change at all. Here it does change, and it changes in the same vein as what we did in the error components model, where we had the kind of the random component model, where we had the random component for the cross-sectional heterogeneity, and then we had the remaining term, and that remaining term became spatially autoregressive, right? Here we're going to do the same thing. We're going to make, in each equation, the error term is spatially autoregressive. Then we transform this into its reduced form. Then the cross-equation correlation pertains really to these remaining error terms. So each of these UTs are the ones that are cross-equation. So in essence, we look at the correlation between epsilon at t and epsilon at s, but because these matrices are constant, they don't, we don't have to worry about them. It's really, the randomness is only in the UT part. So the cross-equation correlation is, the sigma t is from the u, which is what we've been calling the idiosyncratic error term, right? The remainder error term. So it's the same idea as we've always done. When we have an autoregressive error process, we put it in the reduced form. Just to keep our notation simple, we're going to call this B. So in the lag model, we call it A. Here we call it B. So it's B inverse times U. So then with the cross-equation covariance for the U's given by this expression, we can put the whole thing together, and we see that the cross-equation covariance between equation T and S is a T by T, it's an n by n matrix, sorry. It's an n by n matrix because it's cross. So let me step back a second. In the standard case, there's only a scalar because the covariance is the same across the whole cross-section. The covariance between time t and s is the same for all the observations. But because we now have a spatial autoregressive process, that's no longer the case. If you remember the separability idea that we started with a couple of lectures ago, where we have, on the one hand, the time covariance, on the other hand, the spatial covariance, and then the space-time covariance is by putting the two together. So this is an example of this, where we have the, if we go back, this is the spatial covariance using the B. And this is the time covariance with the sigma t. So now we put the two together and we have the space-time covariance. So that's why this is not a simple scalar, but it's actually an n by n matrix that is no longer diagonal. So it's no longer sigma ts with an I, identity matrix of dimension n, but it's sigma ts with the product of these two monsters here, these two inverse matrices, which is really, after some matrix algebra, would be B prime B inverse. But you still have to do the inverse. So the full expression then is something like this, where you have the B in front and the B prime in the back, which shows us again the combination, the space-time dependence comes from the combination of the time dependence with the spatial dependence. As two separate parts, separability. Right? So then, how do we estimate this? Again, this is a very general principle, but the devil is in the details, as always. So if we write this out, we can show, this is why I wrote it this way. If you look at this, this is going to be the big part in the middle, right? This is the variance covariance matrix. And so this will be pre-multiplied by x here and x prime there. So, but we have to take the inverse. So after we take the inverse, it becomes B. Right, this is the same thing we had in the spatial autoregressive error model. The variance had an inverse, so then after we take the inverse, it's gone. And that's the same here. And that's what led us to spatially weighted least squares. So these x prime, b prime, and bx are the spatially filtered x variables. It looks exactly the same as the expression for a single equation, but it applies to the full system, to all these stacked x's. And the same with by, that applies to all the stacked y's. And then by extension, the spatially filtered error terms, which then go into the sigma. So the sigma is no longer based on the actual error terms, but on the spatially filtered error terms. That's the big difference with the standard model. So the error parameter is in here in the filter. It's in here in the filtered residuals or error terms, and it's in here in the filtered y. But once you have the parameter, you get the filters, and this is just like spatially weighted least squares. When we saw, once we have the lambda, we're in business. We make these spatially filtered variables, and then it's just OLS on the rest. So here's the same thing. Once we have the spatially filtered variables and the spatially filtered residuals, or I should say error terms, but then they become residuals to estimate the sigma hat, then we're in business. Everything else is just standard. Of course, where does the spatial parameter come from, right? And so again, we have two strategies. The one strategy is an extension of the Collegian-Prucha GM approach. It's a nuisance parameter perspective in the sense we don't have standard errors. It's just a consistent estimate. And the other one is maximum likelihood. It's going to be a bear again. So the GM setup is that we basically set up a separate set of moment equations for each equation, which gives us a different lambda for each equation, a different spatial autoregressive coefficient. So we run the standard SIR regression. We get the residuals. We stick the residuals in these GM equations. We solve for lambda. We use lambda to make all the spatially filtered things, including the spatially filtered residuals, which give us a new sigma hat, and then we run the whole thing again. The moment equations, we should recognize them right away. They're exactly the same as we had for the spatial error model. The only difference is that we have a little t under here. So for each time period, we have these, and we can solve them for lambda. We plug lambda into the filters, and we're good to go. Again, Bicel SPREG has this. You notice, as you're already familiar, these estimates do not have a standard error. And you also see that the correlation matrix has changed quite a bit. So that's the main effect. of basically you change the structure of the covariance of the errors by putting in this spatial effect first, and then after you filter for that, this is what's left in terms of the correlation. So GM estimation of the spatial SIR. This one is a little easier than the lag model, but still it's pretty complicated. It's the same idea. You see the filtered residuals here. You see the Jacobian t times with a different lambda in each t. After a little bit of algebra, you can again exploit the fact that this E prime E is a consistent estimate for sigma. So we replace these, and this is our concentrated log likelihood. So lambda's in here, lambda's in here, beta's in here. So all the coefficients are in here. This is a complicated optimization problem. We have, you know, a different set of parameters for each time period, and the variance covariance matrix again is a monster. And so then the results, you know, somewhat different from before, but you see basically the same magnitude. 0.5, if you look here, was 0.55 and 0.52 and 0.29 for the correlation. Here we have 0.54 and 0.50 and then 0.31 for the correlation. So not dramatically different, but you do get the inference for the lambda coefficients, just like in the cross-sectional case. So all this stuff can be done. And now that we have our variance covariance matrix, we can actually do our Lagrange multiplier test. Again, we have the same principle. We have the score. We have to figure out this partial derivative. We make lambda 0. Then we have the information matrix. We plug in lambda 0. And the form is very similar to the other one, but it's simpler because the information matrix actually simplifies. So we have, again, these two parts which are the same but transposed. We have the inverse of the variance covariance matrix, direct product with this expression. So again, the U are the residuals stacked. From residuals from the standard SUR estimation. Remember, we're back in the standard model here. This is in diagnostic in the standard iterated feasible GLS. So we take those residuals. These are n by t matrix. We spatially lag them. We take the product with the transpose of this matrix. This is t by t. So direct product between t by t and t by t here too. And then these things are the traces that we know and love, the trace of WW and W prime W, as well as a direct product of the inverse with the original. Now, this, unlike its matrix product, is not an identity matrix, right? So by definition, the matrix product of a matrix with its inverse is an identity matrix. But this is the direct product. So this is the element of the variance of the first equation, the inverse of it, not the inverse of the variance. The element in the inverse matrix that corresponds to that multiplied by the variance in the first equation. So it's a little bit different. Again, this has t degrees of freedom. So it's fairly strict. This one is actually very straightforward to do because you don't have this really complicated variance term. You just, these things, these t by t matrices are standard output of an SUR regression. These traces are a little bit more difficult, more challenging to compute, but nothing we can't do. So this is really easy to compute. But as I said, this is a little bit different than testing equation by equation. This is really, the null is that all t of them are 0. And so the alternative is that any one of these could be non-zero. And in my experience, it's been really hard not to reject a null. You know, and so, again, you have to think about, is this really that useful a test? Because, you know, one thing that you can do after you've estimated this framework is you can introduce, at least with the maximum likelihood one, you can introduce tests for constancy of lambda over time. And this is empirically often a very interesting question. For example, there have been hypotheses out there that the strength of the spillover changes over time. And either because of increasing network effects increases over time, so because the networks become stronger or the communication becomes stronger, you know, internet, Facebook, all that kind of stuff. And so then there's faster spillover. And, you know, there have been interesting applications of this in looking at the banking sector, you know, how financial crises spread. And do they spread faster now than they did 10, 15 years ago, this kind of thing. So these are testable hypotheses where you can put in a spatial lag model or, you know, typically at 2 periods in time, and you see whether these coefficients of rho are the same or are different, go up, go down. You can test directional effects as well. And then the advantage of this in a treatment effect analysis is that you can explicitly take into account both temporal correlation between the equations as well as potential cross-sectional correlation between the observational units. And this is always in causal analysis a big issue. You have this, it's called the Sutva hypothesis assumption, S-U-T-V-A. I never can remember what exactly it stands for, but basically it's that you can't have any correlation between the treatments and the controls. They cannot influence each other. And so if your analysis is at the aggregate level, oftentimes that's violated. And so one way to correct for that is to explicitly account for spatial autocorrelation in these models, and that can sort of, in some sense, correct for it. And then you can look at, you can test both constancy of coefficients of before and after, as well as between treatment and control, and, you know, treatment before, treatment after, control, and you can do the whole DID design very nicely, taking into account cross-sectional dependence as well as serial dependence. Okay, so that's it for today.